Hi, my name is Courtney Lamb, and along with April Taylor, we are going to be presenting this module, which is about algebraic thinking and how we can develop this in students. Please make your way through the slides, and the slides will automatically move forward unless you press pause. From time to time, you may be asked to pause and think or click on something to open a video. Take these moments to do the problems and reflect, and this will help you with your any assignments or reflections for this module. Many people view algebra in a pretty negative light because it has traditionally been taught as disconnected from both life and logic. People have rarely seen the motivation for the algebra they did in school, which was largely a relic from the mid 20th century assumption that we would need lots of people to do computations by hand for engineering, science, space exploration, etc. We want to stress that it is not the fault of the public that algebra is so hated, nor is it the fault of math teachers, who are typically the people who both really loved algebra for algebra's sake and are also working from curricula that continue to present algebra in an outdated way. In general, this cultural animosity toward algebra has been fostered by a very narrow definition of algebra as a set of procedures, often disconnected from people's experience. To make matters worse, that narrow definition is used as a gatekeeper to both higher education and careers, most of which no longer require much algebraic manipulation by hand. There's no reason a person should be blocked from being a nutritionist because they can't factor a trinomial or graph a rational function, but it happens every day. But this is changing, and it's a topic of current discussion among the National Council of Teachers of Mathematics and is somewhat addressed by the Common Core standards. Ironically, as computers make algebraic modeling more accessible, the need for algebraic thinking is actually increasing. From agriculture to finance to geology, people need to understand how to model a situation, even if a computer does all the ugly manipulation. For example, we might look at the relationship between water applied and corn yields, or use physics and math to create a model of when and how a volcano might erupt. Even if mathematical modeling isn't part of a student's future career, being able to understand the world mathematically can help us decide whether to buy or rent a house or and identify predatory loans. If you think about a traditional algebra textbook, this is exactly the flip of where most of the time was spent. Algebraic manipulation was the focus, and students were rarely, if ever, given opportunities to think about how to model the real world. In these two examples, being able to understand and develop the model is what's key. For example, in the corn example, we need to understand why we would choose a certain type of equation and what the model the computer finds means within the context of the problem and know if the computer's results make sense. Likewise, in the magma chamber example, we need to understand the key factors or variables that influence the pressure inside the chamber and how we can use physics to create an equation that can be used to study the volcanic system. Many math education researchers have shown that people are generally capable of algebraic thinking. There are certainly some people who have specific learning disabilities that can put up additional barriers around mathematics in general and algebra specifically. But broadly, the idea that there are a select few math people and everyone else isn't just isn't true. Everyone is a math person. However, just saying that affirmation to your students that everyone is a math person isn't enough. There are specific activities we can use to ignite and foster algebraic thinking as early as kindergarten, and ways we can scaffold algebraic thinking throughout the student's K 12 experience. We can help students use algebra to better understand their world. This module will give an overview of some of those methods. In this module, we'll first discuss what it means to see the world algebraically. Then, we will look at exploring relationships and solving equations. At the end of this interactive model, we'll pull all the ideas together and discuss the assignments for this module. What does it mean to see the world algebraically? This is what we want for our students, but what does it look like? The National Council of Teachers of Mathematics has these four big interconnected ideas: represent relationships between quantities, use symbols to represent and analyze situations, understand patterns, and lastly, analyze change in different contexts. So, one can think of algebra as a way of using symbols as a shortcut for understanding relationships, patterns, and contexts. There's a big disconnect between this, what algebra should be, and what algebra is often perceived as, which is often some version of solving for x. One way to think about algebra is in terms of the ways we use variables. Variables can be used in many ways, but we'll focus on two interconnected meanings. We can use variables, letters that stand for numbers, to explore relationships. In this case, variables live up to their name, variables as varying quantities. We can turn a variable as varying quantity situation into a variable as unknown situation if we nail down one of the varying values. We'll use these ideas to move through the rest of the module. Let's start by thinking about how we can develop algebraic thinking by exploring and generalizing relationships. For the task, make sure you take your time moving from slide to slide. Spend the time understanding the questions and the math. This will help you in your reflection. Let's start with this task. You're looking for the total outside perimeter. Take a moment in your notes to think about how you might approach this or how you think young students, maybe 6th or 7th grade, might approach this problem. What are a couple ways you could figure out the perimeter without counting by ones? Write it in a numerical expression. We've worked with several middle school teachers who tried this with students. Here are some ways they thought about it. Such problems drive home to students that there are many ways to see the same idea and presses them to start to generalize their thinking. Pause for a moment to see if you can interpret each expression by how the parts connect to the visual. For example, on the first expression, what's the +2 on the visual? What is represented by the 5 or the 4? Do that for each expression, then move on to the next slide. Next, let's look at three more questions. First, imagine now that we double the number of hexagons to 10. Again, what's a number sentence that would help us find the perimeter of the hexagon train? Next, if a hexagon train has a perimeter of 30 centimeters, how many hexagons would be in the train? And lastly, how could we find the perimeter of any hexagon train? What are different ways that students might see this? Again, you might want to solve this in your own way or think about how 6th or 7th grade students would approach these problems. Let's look at the train of hexagons first. One thing students are likely to do is just double their original perimeter for the 5 hexagon train. But that won't work because the hexagons don't all contribute the same amount to the perimeter. If we double the 22, we could have 4 hexagons that contribute 5 centimeters and 6 contributing 4, which doesn't match what we actually see. Instead, we hope students will discover that, for example, these two ends will always contribute 10, and the ones between will always contribute 4 centimeters. This problem is meant to help students notice patterns, like every time we add a hexagon, the perimeter goes up by 4. But this problem also helps us understand the underlying structure that gives us that pattern. In other words, what's changing and how, and what's staying the same and why. In this case, we could think of the ends as staying the same, and then we're just adding hexagons in the interior. This is a crucial step in developing algebraic thinking. As for the perimeter of 30 centimeters question, students might use a guess and check tactic, adding on one hexagon at a time to the train until they get to a perimeter of 30. Hopefully, this would reinforce the pattern of adding 4 each time. Alternatively, some students might think to take away the ends and then divide by 4 to see how many middle hexagons there are. Both of these approaches start to reveal the underlying pattern and structure of the problem. This is also a bridge to variable as representing an unknown. Again, you might want to solve this in your own way or think about how 6th or 7th grade students would approach these problems. As you work, think about the purpose of each problem. The last question about finding a way to know the perimeter of any hexagon train is asking us to generalize. Tables and graphs allow us to represent multiple trains at once, so we can again look at patterns and structures. In both, we can see that for one increase in the number of hexagons in the train, we see a positive 4 increase in the perimeter of the train. These are expressions we've seen students develop representing the perimeter for n, which is the number of hexagons in a train. They are all equivalent, meaning for the same value of n, they will all give the same perimeter. And a little algebraic manipulation will boil these two down to 4n plus 2. Pause here for a moment and think about how a student might see each expression within the actual hexagon train. The first expression represents the thinking of a student who sees each hexagon contributing 4 centimeters from its top and bottom and then adding the two sides. The middle expression represents the thinking of a student who knows each hexagon individually has 6 sides and then takes away these interior spots where the hexagons meet. They figure out that there are n minus 1 of these spots and you have to take away 2 centimeters for each of those. Lastly, this student is the one who sees that the two end hexagons each contribute 5 centimeters for a constant of 10 centimeters. And then there are n minus 2 middle hexagons that each contribute 4 centimeters. This act of connecting the symbolic representation back to the picture serves a few important purposes. We can press students beyond just seeing a pattern that seems to work to using the structure of the problem to really prove that their rule will work in all cases. We often see students who are convinced that their rule will work for a pattern or a generalization problem after trying it 3 or 4 times. What we actually want to emphasize is that the rule works because of the structure of the problem. In this case, we need to understand what is changing and what is staying the same as we add more tiles. The other reason this act of connecting the symbols back to the picture is important is that it helps students connect the mathematical symbols to the real world. We need students to believe that their ways of seeing the pattern are valid and connect to more formal algebraic representation. One way we can explicitly focus on certain concepts is to provide opportunities for variation. Variation of a problem is the idea that we can keep using the same general context but make small changes to emphasize certain concepts. In this problem, we can think about how our equation, table, and graph would be similar or different depending on the shapes in the train. Varying one context, this can be particularly important for ELL students who are already invested with the vocabulary of the original problem. Of course, it's also important to look across contexts and find similarity, but varying a single context can get the most bang for your buck out of one problem.
Now let's switch gears to look at solving equations, thinking about the variable as representing an unknown quantity. When we ask students what number goes in the box in an equation like this, Frequently, we'll see them add up numbers to get to 55, or maybe they'll even add all of the numbers and get to 75. These answers indicate a misunderstanding about what that equal sign really represents, that the two sides have the same value. If we understand the true meaning of the equal sign, then we would get the answer of 35 because both sides need to have the value of 55. A relational understanding of equality means students understand that the equal sign represents a relationship between two sides of the equation. They correctly understand that equality means the same as. Whereas a computational understanding of equality is where students see the equal sign as meaning compute or get the answer. This incorrect understanding of the equal sign comes from seeing problems only in the form of 3 plus 4 equals 7, or even just using the equal sign on the calculator. We've had high school teachers who are working with struggling students give this problem to their classes. And what was really eye opening for them was that students struggling to understand algebra frequently had a computational understanding of equality. And that makes sense. If you don't understand that the equal sign means that both sides have to have the same value, algebra quickly becomes an act of memorizing the rules and procedures that have no basis in logic. A couple things that we should know. Students can start developing this kind of relational understanding of equity as early as kindergarten through problems like this or problems with smaller numbers, even enacted with blocks. So, presenting students with different forms of equations with different elements that are missing will help to build that idea that the equal sign means the same as and not, here comes the answer. We also know that this is an idea that needs to be repeatedly revisited across grade levels. We have seen students in middle school who'll still answer this question incorrectly, but they had worked on developing a relational understanding of equity in earlier grades. So it seems that subsequent years of fact fluency and calculator use sometimes might undo some of that hard work. So coming back to these types of problems repeatedly is important. Another way we can develop students' relational thinking before just jumping into procedures for solving equations is with a visual equation puzzle. The idea here is to bridge from the first visual to the second visual. This first one is just to set the stage. One triangle is worth two squares. Nothing tricky about that. The second builds on that. And all we've done is add a square to both sides, so a triangle is still worth two squares. Sometimes we'll see students actually draw the squares on top of the triangle so that they can visually see the equivalence of both sides. Now let's take a look at each of these. How many squares is each triangle worth? So before we pause to work these out on our own, two quick notes. Each line may have a different answer, and we could end up working with fractions. So pause here for a moment and think through these problems. So generally, we tend to use these kind of problems in class as a string. That way, students can use strategies developed in the earlier problems for later problems. Students tend to see this first problem in one of two ways. Some will recognize that the two squares are the same on both sides, and then recognize that each triangle must be worth two squares in order to have the same number on both sides. Other students will remove the two squares from both sides and then divide both sides by 2. The first approach really emphasizes that idea of the equal sign meaning the same as, and the second connects to procedures for isolating the unknown. That idea of recognizing and removing what's the same on both sides is useful in the second problem. We can take one square and one triangle from both sides to see that each triangle is worth one square. And we can use that same thinking again on the third problem, where each triangle must be worth half a square. This last problem tends to be the most challenging. Starting off by taking away what is the same, we end up with 3 triangles are worth 2 squares. Students will often cut each of the 2 squares into 3 pieces and kind of sort of deal out the thirds to each triangle, letting us see that each triangle ends up being worth 2/3 of a square. As students get more comfortable with these puzzles, we can start to transition them into symbolic representations of their strategies. Going back to this problem, we can use the symbols to show that 2 is the same as 2t plus 1, and then reflect each step with symbols, connecting the steps to what the students visually did to solve the problem. Students will need to think symbolically and eventually will need to deal with negative numbers and ugly decimals that can't be drawn out. So we want to make those explicit connections from the visual to the symbolic, moving back and forth. Balanced scale reasoning is another model for getting at the meaning of equality. Asking, for example, for 3 true equations about the cans can press students to see relationships between the two sides. These are a few of the equations people commonly develop for this question. One important step, once we know the weight of a can, is to go back and verify that both sides have the same value. One powerful question about this model is whether the scale stays balanced if we double both sides. The answer is yes, because the sides have to weigh the same amount in the first place. But because what we are adding to both sides is not visually identical, sometimes students will say no. The point here is that we're developing some initial understanding of how we can create equivalent equations by adding or subtracting the same amount from both sides or multiplying both sides by the same constant. These are key ideas in being able to fluently solve equations. One note from experience: this balance idea seems to really resonate with many students, but not all. For some students, that bar model, where length is visually the same, seems to help illustrate the idea of equity more clearly. Here we're going to watch 2 videos that discuss how the equal sign is misunderstood and misused. In this last major problem, these ideas of variable and varying quantity and an unknown are kind of put together in one problem. Take a moment to pause here and solve this problem using any informal method that you like. We're going to assume that the tacos all have the same price and that the drinks all have the same price. We're going to look at the 3 most common approaches that we see students use that actually make use of the presented visuals, and then we'll relate those to some more formal methods. Pause here for a moment and think about what this person did. How is it similar or different from what you did, and what made this approach possible in this particular problem? This person found a smaller equation or unit to work with. They realized that 3 tacos and 3 drinks is $12, and that must mean that a taco drink combo is $4. They then use that in the other equation, replacing the 2 taco drink combos with $4 each. So we now know the 2 leftover tacos are $5.50, and 1 taco is $2.75. So going back to the $4, we can subtract the cost of 1 taco to get the price of the drink, which is $1.25. Eventually, we want to start connecting these methods to symbolic representations, seeing algebra as basically a shortcut to representing the problem. So instead of drawing out pictures, we could use letters and numbers. This is how we hope students come to see algebra as a shortcut that makes problem solving easier. Eventually, that idea of finding a smaller equation to work with might become the general approach of substitution, where we solve for just one variable in terms of the other and substitute it in. But connecting back to students' informal strategies can both give them more tools for solving equations generally and make conventional approaches more real and connected to their experience. Take a moment and pause to look at method 2. And think about how this method works and how is it different from method 1. In method 2, we're basically repeating each food order until we have the same amount of some food item. Rather than looking for a smaller equation, we're scaling both equations up. In this case, if we triple the top order and double the middle order, we end up with much larger purchases that each have 6 drinks. That means that the different price for those large orders is due just to the difference in the number of tacos. There is a difference of 6 tacos, so those 6 tacos must represent the difference in price, $16.50. So each taco is then $2.75. Again, algebra becomes the shortcut for this approach. We can think of setting up the equations and tripling one and doubling the other until we have 6D in both equations, and then subtracting to find that 6 tacos is $16.50, and then dividing it like we did before. We can generally use this approach, scaling each known equation up or down until we have the same number of one of the unknowns. This approach eventually becomes the elimination strategy for solving systems of equations. All right, so let's take a look at what this person did. Pause and think about how is it similar or different from methods 1 and 2. In method 3, we look at the difference between the two original purchases. The only thing that's different is that this order swapped out a drink for a taco. So this difference in price must be the difference in the cost between a drink and a taco. A taco is $1.50 more than a drink. We could use that to make a smaller equation as in method 1, t equals $1.50 plus d, and substitute. But this person took a different approach. They just kept swapping out a drink and taco until they had all tacos. So 6 tacos is $16.50 again. Each taco is $2.75, and each drink would be $1.50 less than that, or $1.25. Method 3 really doesn't have a formal version in algebra other than noticing that t equals d plus $1.50 and substituting in. But it does show really excellent reasoning and use of patterns and structure. We might even have a student who uses an organized form of guess and check. For example, guessing at values for the taco and then seeing if that results in the same drink price for the two different equations. Maybe they test out $1, $2, and $3, noticing that the drink prices get closer around $2, but then get further apart again in moving from $2 to $3. So the correct price must be somewhere between $2 and $3. They try out $2.50 and notice that the difference is 25 cents again, the same as $3, but in the other direction. So the answer should be between $2.50 and $3, or $2.75. This would be really inefficient, but really solid reasoning. What's nice about the kids who use guess and check, even if they don't do it as efficiently as what we just saw, is that their methods generally connect with the way we can solve this problem through graphing. We can graph these two equations on a graph of taco price versus drink price and see where they match up. Given how easy programs like Desmos are, graphing methods are becoming some of the most efficient ways to solve algebra problems. If you want to see this graph in Desmos, click on the link. Going back to think about how we use variables, given just one of the two visual equations, this would be a variable as varying quantity problem. We could list out all the possible prices of tacos and drinks that would make this number sentence true. But having both pieces of information means we can nail down the actual value of a taco and a drink, turning this into a problem where we are looking for the specific values of unknowns. This is a step that comes in 8th grade and is one of the primary ways that algebra gets used in real life. What values will work to meet a set of constraints? In this course, we've been focusing on this idea of productive struggle. This problem is a good illustration of how we can take a task students may shut down on and make it accessible enough to provide productive struggle without giving the solution strategy. For example, if we had started a unit on systems of equations by just presenting this, many students might have just shut down, and the response of traditional algebra would just be to tell them ways to do the problem. But we can scaffold students in reasoning through this problem by doing a series of intentional moves. Go ahead and return to the module for your next activity.